Hello, I'm Ravindra Bagul, and today I'm presenting on utilization of 3 Doppler weather radar to study the atmospheric convection. So here we have a content of the table. Uh, in this presentation, I'm going to introduce about the atmospheric convection, a little bit introduction about the atmospheric convection, past studies on the convection, objectives of the study, Doppler radar system, and the data set which we have used to study the atmospheric convection, and some of the plan of work that we have, and at the end we have references over there. So in the introduction part, atmospheric convection is, as we know, that thermally driven turbulent mixing of the atmosphere. There are many types of convection that we can see, like dry convection, wet convection, shallow and deep convections. So the atmospheric convection is a dynamic concept that refers to a rapid, efficient and overturning of a fluid under gravity in the atmosphere that requires to be neutralize an unstable vertical distribution of a moist static energy, and the convection can lead to active cumulus and cumulonimbus clouds whose precipitation is partly stratiform and convective type. So in figure we can see the vigorous convection over there. This we have the air motion in the arrows, left hand side arrows air motion, right hand side air motion. The wind speed is shown here 1 to 10 meter per second, and this is the precipitation trajectories with a height that precipitation growths that dominated by the collection. These are, we have radar ecotop, the convective radar ecotop. In the convective radar ecotop we have the outer line, we can see this is the maximum reflectivity over there. So the stratiform precipitation is that fairly homogeneous in the horizontal manner, and that having the layer structure in the vertically oriented columns rather than the horizontal layers produced by the bright band in the stratiform precipitation. That convection refers to the transport of heat, we can say the transport of moisture also by the movement of the fluid. In the atmospheric convection, the part of a heat transfer that's that's known as the sensible heat, and it's the heat might be sensed with the thermometer. That's why we call it as a sensible heat. And if the water vapor is in the air, the possibility exists that latent heat will be realized. This heat is called as the latent heat, because one cannot sense it until the water vapor condenses. So this is we have the old convection, and this is the air motion at 0 degree we have, and wind speed is mostly about 1 to 2 meter per second in the old convections, and the precipitation trajectories in the stratiform precipitation manner is like with height is at 0 degree Celsius. This is some aggregation and diffusion we have. Below the 0 degree we have melting rain, and the radar ecotops for the stratiform precipitation is like a very weak horizontal gradient we have, and the bright bands we can see over there. So in the introduction of atmospheric science, we can atmospheric convection, we know that the atmospheric convection differs to the shallow and a deep convection. So one of them is the shallow convection. This is the thermally driven mixing of a turbulent where the vertical lifting is kept below the 500 hectopascal, that is the vertical level, and the shallow convection requires the low convergence, that we can see in the diagram. The figure shows at the ground level, that the low level we have a convergence, middle level divergence, and the high level upper level convergence we can have here. So the shallow convection echoes can produce as much and sometimes more rainfall accumulation as the deep convective sense as compared to the deep convection. And in the deep convection figure exactly shows us that it requires the low level convergence and the upper level divergence. There is no middle level convergence or divergence over there, and generally deep convection requires the low level convergence. Okay, and Next, we have the past studies on the atmospheric convections. There are more studies, but some of we have selected from the other studies. So convection in the atmosphere forms different types of clouds, some of which produces heavy precipitation and intense lightning. So variables like convective cutoff height and the height of 30 dB reflectivity contour were used to discuss the vertical structure of atmospheric convection, that and the characteristics of microphysical and lightning properties, and that is well discussed in a Demott and Rijal study. Also in the study of Carey and Rutels in the 1999, the co-evaluating microphysical kinematics and electrical properties of multi-cell thunderstorm using the Doppler radar, 6 shape orientation and thermodynamics information of hydrometers, that is obtained by the polarimetric variables. So using the Doppler radar, they have observed the microphysical properties of the electrical and other microphysical kinetic properties of the thunderstorm. So that we have used to study the thunderstorm properties, electrically and microphysical properties. Again, in the other studies, like how the convective storm microphysical and dynamical processes affects the production of lightning, and which includes the flash rate, strike type, polarity. Is it positive or negative? Is it a ground base or cloud to ground, or other lightning strikes? And the flashes are typically intercloud flashes. So that is well discussed in the studies of Walkman and Reynolds in 1949, Livingston and Creeder 1978, Goodman et al. 1988, Williams et al. 1989b, Mayer and Creeder 1986 described, and also in the Lang and Rutels paper 2002. So this we have the objectives of our study. So the convection in the atmosphere forms the vigorous types of clouds, as we know already, and the ground-based radars that we are using the ground-based radars that provide the unique data set containing valuable information on the air motions and the precipitation within the clouds. So these are two, or we can say the few objectives of our study. One of them is to study the horizontal and vertical structures of the clouds, so we can have the more information about clouds, like vertically and horizontally, how they are forming, how they are changing, how they are having the variations in the vertical and horizontal manner. And other one, we have the microphysical properties of the clouds. After studying the horizontal and vertical studies of the structures of the clouds, we can observe the microphysical properties of the clouds. So this is the little bit information about the radar system, Doppler radar system we are using over here. One of them is the expand radar, that also known as the precipitation radar. Expand radar having the 125 kilometers surveillance area in the radius, and it has the frequency of 11 dB, and the expand radar system is a trailer mounted transportable simultaneous dual polarization, that's known as a seat pole Doppler weather surveillance radar, that is DWSR. The digital signal processor DIMA third employs pulse pair Doppler processing technique and produces standard moments and advanced polarimetric products via enterprise Doppler graphics environments. That is the software or application software we are using over here. And next we have the K-band radar, that is known as the cloud radar. The K-band radar is that is a K-band radar is a scanning of it having the frequency of 35.29 gigahertz, and that it can sense about 45 dB at 5 kilometers. It having the very less surveillance area of about 25 kilometers in the radius. It is lesser than the K band. It has a less minimum range than the X band radar. So here we have a data sets like X-band and K-band radar, precipitation and cloud radar we are using over here, that are mounted at that deployed at the Mandadev in the Mahabaleshwar at the 1.3 kilometer from mean sea level. And the radar data that includes various Dopplers and polarimetric variables like radar reflectivity, radar radial velocity, and differential reflectivity. And the K-band radar operates in a PPI mode. PPI mode, that is a planned position indicator mode, by varying the azimuth angle of the radar beam by maintaining a fixed elevation angle, and alternatively horizontal to horizontal scan mode was also performed by varying the elevation angle of the radar beam by maintaining a fixed azimuth angle. And the scanning strategy usually involves the 12 ppi scans at the constant elevations, and 2 horizon to horizon scan at a fixed azimuth of 239 degree, and a 5 minute of vertical pointing scan. So in the interval of a 5 minute and 12 ppi scans in the 1 hour, so we have uh, 5 ppi modes and a 5 we can say the vertical pointing scans in a single hour. And in the X-band radar had a hybrid scan strategy involving PPI scans, that is from 0.5 to 90 degrees in the from horizontal to vertical, like 0.5 to 90 degrees, and a total of 18 sweeps of each volume that follow by RHI, that is a range height indicator, in the azimuth of HASCPL, that is high altitude cloud physics laboratory, that is also mounted at the 1.3 kilometer of from the mean sea level, that is established by the Indian Institute of Tropical Meteorology at the Mandadev. This is how the topographically looks the radar image. It is showing the radar, the black circle is showing the radar surveillance area of 251 kilometers overall. This is the Mandadev where the radar is mounted, and this is the HSCPL where we have deployed other instruments like rain gauge and other sensible instruments. This is how much farther from the Pune, and this includes this can observe the Western Ghats data, and that is the windward side and leeward side. We can have the great data from the radars. And here we have the actual image of radar. So in the image B, we can see the X-band radar and the K-band radar. This is the K-band radar, and this is the X-band radar. So from this ground horizontal 0.5 degree elevations, we can have up to 90 degree. So this is how the X-band radar works. And now we have a plan of work, what we have decided to work. So this is the 3D high resolution data obtained from the cloud and precipitation radars, that is K-band and X-band radars, and other supporting instruments like lightning location network we have, and radio sonding. So these data sets would help to understand the dynamical and microphysical aspects of the tropical convection. So we are in the tropical region, so we can easily observe the tropical convection aspects or microphysical aspects of the tropical convection by using these data sets. So the cases will be selected from the radar and lightning location network to analyze the dynamical and microphysical as well as the electrical properties of the convection. So like how the lightning is changing over there, how the flashes we had that time, and how the lightning is occurring in that time. So these are some examples like to identify the convective and stratiform features, and whether we have a convective precipitation or a stratiform precipitation, that we are going to identify, and also going to estimate the convective crop heights at 0 dBc, 30 dBc, and the thresholds using the radar data, and determine the occurrence and flash rate of cloud to ground, that is CG lightning, inter-cloud lightning from the lightning location network. So the radius only profile from high altitude cloud precipitation laboratory at Mahabaleshwar. So that will be used to get the thermodynamic state of the atmosphere in which the convection that starts to build some. So it would be the important to see the relation between mid tropospheric humidity and the formation of the deep convection. So once we have the radar data, after that we can partition into the convective and stratiform features. So there are methods that will apply to depict the vertical and internal structures of the convective echoes. So like we have here the convective echoes and the stratiform echoes, how the heating rate is changing with the height. So in the convective echo we can see it is mostly the positive way, and as the height increases up to the middle level it is getting increased, and after that is suddenly in the same manner it is decreasing. But in the stratiform echo, it is starting with the negatively it is increased, comes to zero, goes to positive increase, and then again it is decreases. And but in the as we compare it with the divergence against height, so in the convective echo it is starting with a negative, comes to zero, and again it goes to increase. So once we have first we in the convective one we have convergence, divergence, and again the divergence. So positive divergence, negative divergence to the positive divergence. But in the stratiform manner we only have it is starting with the positive divergence, comes to the middle level, comes to the negative divergence, that is the convergence, and again it comes to the divergence. So in the stratiform, as first we have seen that in the stratiform manner, stratiform precipitation, stratiform echoes, we have first the low level divergence, middle level convergence, and the higher, that means the upper level divergence. But in a convective echoes, in the convective manner, we have the convergence at the lower levels, no middle level or no middle level convergence divergence there, and at the end, at the higher level, at the upper level, we have the divergence. So that shows again, that proves here. So this we have two convective features, like 30 dBz contour. We have the left hand feature that has the 30 dBz contour, that the right hand feature responding to the greater liquid and ice water masses above the freezing level. So this is the freezing level we have, and this figure depicts two convective cells with the same echo height but the different internal structures, as that's suggested by 30 dBz contour heights, because the two cells that have the identical heights, that is the same height the two cells have, and the presence of greater than 30 dBz reflectivity above the freezing level is often that associated with the lightning production, so that we have the enhanced scattering over here, and it has the same contour level, but some of the internal properties that the left hand side has the more, and the right hand side has the lowest. And again we have the vertical cross section of the convective feature, that is composed of 4 convective cells. So in the vertical manner it is a height. Here we can see this is the outer line is the maximum height, and the inner side, the gray side, it's the maximum 30 dBz contour height. So the upper dash level shows and the lower dash level shows the mean height and mean 30 dBz contour height respectively, and these are the 4 Cartesian grid columns. So that is how where the reflectivity greater than the 30 dBz contour heights and rainfall that is associated with the convective features, categorized by their maximum height, may be several kilometers higher than their mean heights, that is heavy dash lines over here. So schematically how the convection looks in the radar data, that these images are obtained using GRADS software, that is the graded data analysis system. So radar data, we observe that on the particular date, the 4th October, at the time 11:29:27 seconds, and this is the longitude and latitude we have over the domain of the radar. We have the convection over here, that is the this is showing the reflectivity. Actually, this is showing the reflectivity from the radar. So we can say the if it has more than 40 dBz reflectivity, so there is a convection occurs. So easily we can say by seeing this figure, here we have a convection, and as compares to the other figures, this figure shows the ecotop heights at 0 dBz, this is at 10 dBz, and another at 30 dBz. So as compared to other two figures, the 0 dBz cutoff has the more values, 10 dBz has median values, and 30 dBz it shows the very lower values, because it is showing up to the 5 or 4 dBz. And over here we can see in the 10 dBz we can see up to 12 or 14 dBz, and in a 0 dBz cutoff side we can have the values over 16 dBz. So this is how the convection figure. Again we have another case from the same date at the different time, 12:20:24 seconds. So we can see the convection over here at the other side of a windward and other side of a leeward. So usually we have the more convection, more precipitation, and over the windward side, the same as the same figure drawn for the different time, like 0 dBz cutoffs, 10 dBz cutoffs, and 30 dBz cutoffs. And this is the references we have. So we have referred these papers to study over atmospheric convections. And thank you.